Next, what we're going to look at are bar graphs, where a bar graph represents measurements or amounts of some given type of data or multiple types of data, depending on what you're looking at, where you have the amount represented on one axis and then something else represented on the other. Say if you're looking at the amount of something over time or a comparison between two amounts. So the example we'll look at here is one where we have a bar graph that lists data on life expectancy in the United States by gender since the year 1950, where we have a couple different parts to this problem. The first thing we want to do is estimate the increase in life expectancy for women, rounded to the nearest hundredth of a year each subsequent birth year. And when I say a few things, I mean that in the sense of it's not just one thing to look at this graph to be able to get the value we want. It's going to take a bit of thought, it's going to take a bit of work. So to do that, first thing we need to do is find the change in birth rate. Excuse me. Find the change in life expectancy. I said birth rate. Weird. Anyway, find the change in life expectancy from 1950 to 2020. What you do is just look at both of those bars for women in each of those years. So in 1950, the life expectancy for women or females was 71.1, while in 2020 it was 81.9 year. So put these two pieces of information together, and the change in life expectancy was 81.9 minus 71.1, or 10.8 years of life expectancy. Would that be 10 years and 8 months. Next, we need the change in time. So to get the change in time, we're going to look at what happens in that graph. We're going to look at the difference in the horizontal axis, because here the horizontal axis tells us about time, where we're going from 1950 to 2020 for a change in time. Is 70 years specifically. So to find what we were really looking for, the increase in life expectancy for each subsequent year, what we need to do is take the change in life expectancy and the change in years and divide them. So we'll take 10.8 divided by 70, and because we're going to be rounding to the nearest hundredth of a year, you get 0.15, where this is years of life expectancy per year. So I'm not going to write the units for that because it's kind of clunky looking, but it tells you the idea that what we're looking at here with this in terms of units is a rate of change in life expectancy as given per year. And then what we can do with this is take this information and spread it just a little bit further. We can take this right here, which tells us the rate of change, and we can use it to find the life expectancy in 2030. I should be more careful with my wording. I shouldn't say find there. I should say predict. is we're not necessarily finding the life expectancy 10 years from now. We don't know if it's going to be true. We're predicting. To do that, there are a couple ways we can go, but the best way to probably do it would be to use all of the information we have. So our starting value is this value here, that in 1950, life expectancy was 71.1. So we have 71.1, and then each year, life expectancy went up by 15 hundredths. So we add 0.015, excuse me, and then we multiply this, since this is a rate per year, by the number of years from 1950 to 2030. Multiply that by 80. Following through with our computations here, we don't actually need to round anymore unless we really want to. We will get that the average life expectancy will be 83.1 years the year 2030. But what we did here was use an example of a mathematical model to make a prediction. I'll talk a bit more about that at the end of this section.